Hello, my name is Fatih Furkan Erkic. In this practice lab, we advise for either explore techniques to evaluate and improve machine learning models. Here's outline, package, evaluating learning algorithm, polynomial regression, bias and variance, evaluating a learning algorithm, neural network, model complexity, regularization, and iterate to find optimal value. To prevent errors from the autograder, you are not allowed to edit, delete non-graded cell in this notebook. Okay. Packages, we will use NumPy, Matplotlib, and scikit-learn, and TensorFlow, Keras. Okay, let's run it. Evaluating a learning algorithm, polynomial regression. Let's say you have created a machine learning model and you find it fits your training data very well. You're done, not quite. The goal of creating the model was be able to predict the values of new examples. How can you test model performance? Split your original data, training and data sets, training and test sets, and develop an error function to create your evaluate your model. Splitting your data sets. Lectures advised reserving 20 to 40% of your data set for testing. Let's use sklearn function train test split to perform the split. Double check the shapes after running the following cell. Generate some data x, y, x ideal, y ideal equals scan data and print x shape, y shape. Let's run it. Plot train and test sets. You can see below the data points that will be part of training in red are intermixed with those that the model is not trained on test. This particular data set is a quadratic function with noise added. The ideal curve is shown for reference. Let's run it. Here's our test data in blues and train data in reds. Error calculation for model evaluation, linear regression. When evaluating a linear regression model, you average the squared error difference of the predicted values and the target values. Here's our J function. Below, create a function to evaluate the error on a dataset for a linear regression model. Okay, let's code in here. We define an error plus equal to y minus I hat okay. And we okay, and then let's run it. Let's write it like in the hint. And then, okay, let's run it like that. That works. And I will pause the video in here for a moment, and then I will continue. Okay, let's continue the video. Here, compare performance on training and test data. Let's build a high degree polynomial model to minimize training error. This will use the linear regression function from sklearn. The code is in the imported utility file. If you would like to see the details, the steps below are: create and fit the model. Fit is another name for training or running gradient descent. Compute the error on the training data. Compute the error on the test data. Let's run this cell. The computed error on the training set substantially less than that of the test set. We print the training error and test error. The following plot shows why is this. The model fits the training data very well. To do so, it has created a complex function. The test data was not part of a training, and the model does not a poor job of predicting of this data. This model would be described as overfitting, high variance, and generalized poorly, because the test error is really big. And here is the predicted degree time and y ideal is the red dotted test set error shows this model will not work very well on new data. But test data was meant to represent new data. You will need yet another set of data to test new data performance. The proposal made during the lecture is to separate data into three groups. The distribution of training, cross-validation, and test sets shown in the below table is a typical distribution, but you can be varied depending on the amount of data is available. Training 60% and cross-validation 20%. Tests 20%. Training data used to tune model parameters W and B in training or fitting. Cross-validation data used to tune other parameters like degree of polynomial regularization or architecture of a neural network. Test data used to test model after turning a gauge performance on new data. Let's generate three datasets below. Well, we'll once again use train and test split from sklearn, but we'll call it twice to get three splits. Okay. Bias and variance. In this section, plot training cross-validation test. Below the data points that will be part of training in red are intermixed with those that the model is trained from. Test and CV. Let's run this cell. The red dots are our training and orange one is CV and blue ones are test. Finding the optimal degree. In previous labs you found that you could create a model capable of fitting complex curves by utilizing a polynomial. Further, you demonstrate that by increasing the degree of the polynomial you could create overfitting. Let's use that knowledge here to test our ability to tell the difference between overfitting and underfitting. Let's train the model repeatedly, increasing the degree of polynomial each iteration. Here we are going to use scikit-learn linear regression model for speed and simplicity. Let's plot the results. Predictions versus data graph in here and error versus degree in here. Plot above demonstrates that the separating data into groups, data the model is trained on and the data the model has not been trained on can be used to determine if the model is underfitting or overfitting. In our example, we created a variety of models varying from underfitting to overfitting by increasing degree of polynomial used. On the left plot, the solid lines represents the predictions from these models. A polynomial model with degree 1 produces a straight line that intersects very few data points, while the maximum degree goes very closely to every data point. On the right, the error on the training data blue decreases as the model complexity increases as expected. The error of the cross-validation data decreases initially as the model starts to conform to the data, but then increases as the model starts to overfit the training data. fails to generalize. Okay, so this is the optimal degree, this point. 2. Tuning regularization. In previous labs, you have utilized regularization to reduce overfitting similar to degree. One can use the same methodology to tune the regularization parameter lambda. Let's demonstrate this by starting with a high degree polynomial and varying the regularization parameter. Let's see the plot. Optimal lambda is around here, and here is the different lambda functions. Getting more data, increasing training sets, and nice. And the above plots shows that when a model has high variance and is overfitting, adding more examples improves the performance. Not the curves on the left plot. The final curve with the highest value of m is a smooth curve that is in the center of the data. On the right, as the number of examples increases, the performance of the training set and cross-validation set converge to similar values. Note that the curves are not smooth, as one might see in a lecture. That is to be expected. The trend remains clear. More data improves generalization. Not that adding more examples when the model has high bias underfitting does not improve performance. Evaluating a learning algorithm neural network. Dataset. Run the cell below, generate a data, split it into cross-validation test sets. In this example, we are increasing the percentage of the cross-validation data points for emphasis. Above you can see the data on the left. There are 6 clusters identified by color. Both training points, dots, and cross-validation points, triangles, are shown. The interesting points are those that fall in ambiguous locations where either cluster might consider that members. What would you expect a neural network model to? What would be an example of overfitting, underfitting? On the right is an example of ideal model, or a model one might create knowing the source of the data. The lines represents equal distance boundaries, where the distance between center points is equal. It's worth noting that this model would misclassify roughly 8% of the data set. Evaluating categorical model by calculating classification error. Here's our second exercise. And below, complete the routine to calculate classification error. Not in this lab. Target values are the index of the category and are not one-hot encoded. We will code in here. Let me check for it before continue, and I will continue the video. Okay, let's continue. We'll create a if condition, and if y hat I is not equal to y I incorrect, incremented 1, and final CLR incorrect over n. Correct over data. Okay, let's run it. And categorization error 0.33, expected is same, and categorization error and expected error is same. Here is model complexity. Below, compose a 3-layer model, dense layer with 120 units, ReLU activation, dense layer with 40 units, ReLU activation, dense layer with 6 units, and a linear activation of softmax. Compile using those with sparse categorical cross entropy. Remember to use from underscore logits equals true. Atom optimizer with learning rate of 0.01. Okay, we'll use TensorFlow Keras layers dense of 110 20 activation value, and let me copy this. With 40 and 6. And in here we define a loss cross categorical cross entropy from logits true, and an optimizer TensorFlow Keras optimizers Atom, and learning rate of 0.01, and I think it's done. Take a warning. Okay, let's use learning rates. Okay, let's begin the test. little complex. All tests passed. This model has worked very hard to capture outliers of each category. As a result, it has miscategorized some of the cross-validation data. Let's calculate the classification error. And it works fine. Here's the simple model. Check this. Okay. Dense layer with 6 units, ReLU activation. Dense units with dense layer 6 and linear. Okay. And compile. Define a loss. Ask the local trophy. Nuggets. True. Then optimizer. Yes. Optimizers. And weight with 0.01. I think that's it. Let's run it and run this. All tests passed. Let's see the model. This simple model is pretty well. Let's calculate the classification error. In simple model 0.065 and 0.007. In simple model 0.059 and complex model 0.109. Our simple model has little higher classification error on training data but does better on cross-validation data than the more complex model. Here is the equalization exercise. And again, ReLU, and we will use kernel regularization TF class. L2 0.1. Let's copy this. It's 40 ReLU and linear one. It's 6. And actually, let me take it from here. Okay, let's run it. Oh, before to put commas. And let's run the test. Let's run the summary. All tests passed. The results are very similar to ideal model, and here's the error rates. The simple model is a bit better in training sets than the regularized model, but worse in cross-validation test. Iterate the optimal regularization value. Let's run it. Let me stop the video in here and I will continue after this will complete. It finished. Let's plot. As regularization increased, the performance of the model on the training and cross-validation datasets converge. For this dataset and model, lambda greater than 0.01 seems to be a reasonable choice. Let's test our optimized model on the test and compare the ideal performance. Our test set is small and seems to have number of outliers, so classification error is high. However, the performance of our optimized model is comparable to ideal performance. You have become familiar with important tools to apply when evaluating your machine models, namely splitting data into trained and untrained sets. Allows you to differentiate between underfitting and overfitting. Creating 3 datasets, training, cross-validation, and tests allows you to train in your parameters W, B with the training set, tune model parameters such as complexity, regularization, and number of examples with cross-validation set, evaluate your real-world performance using the test set, comparing training and cross-validation performance provides insights into a model's propensity towards overfitting, high variance, or underfitting, high bias. Okay, that's for all. I will check here after that. Thank you for watching. Have a nice day.